Hello and welcome back to Calculus 3. So we're looking at limits and continuity. Now that we define a function, we want to see is that surface smooth and continuous everywhere, right? Or we have pitfalls like a waterfall or a cliff or something that we have to be worrying about. Is there a hole, right? A place that is not defined so that, you can just disappear. So continuity is going to be the same thing, same definition, except in 3D, like in Calc 1. In Calc 1 we said continuity at the point, and then continuity at all points. So global continuity. So we have the notion of function being continued at the point, and then the function being continued everywhere. Now, in order for us to define continuity, we first have to be able to deal with the limits in 3D. And that is now a huge headache. As easy as limits were in Calc 1, because you can only approach from left and right, if you were able to understand, like really, what the limit was and how limit operated in Calc 1, the limits should be the biggest joke of your education so far. Because they're visual, you can do them in a chart, and you can do them algebraically. We can't do all of that efficiently like limits. So we start with Calc 1, obviously. So in Calc 1, we are looking at the limit of, say, let's go with a square root of x. All right? So if you are looking at the function square root of x, we pick, well, this should actually go, whatever. Line is a line. So now, what do I have? If I'm looking for the limit at some point A, the limit is this value here, L. So if I'm not seeing you at the street, if I'm seeing you at the train or the airplane, you're sitting next to me, or we're out or the event or something, you're not my student. You're asking me what's a limit, right? Because I heard you teach calculus. Limit is just a y value of the function. It's a fancy way to compute it. Your pre-calculus says f of 3 is 9, let's say, if it's x squared, and you are computing that 3 in x squared, so it's 3 squared, 3 times 3 is 9, and that's it. The limit does the same, has the same answer, but it computes it differently. So the difference between the pre-calculus and calculus, between computing directly and computing with the limit, is the limit is using motion and approach. I call that Romeo and Juliet. So you approach from the left. So the limit goes to, let's say, 4. If the limit goes to 4, that immediately means motion. You are walking towards 4. If you are walking towards 4, that reflects on walking towards 4 here, which in fact is walking towards the answer on the y-axis from that side. That's Juliet. Red for girls, right? Now we have a boy, blue. We have to embrace those stereotypes, right? So now, why do you have a blue shirt? You should have a... Anyway, so now, I know exactly where to go, right? Now we go approach from the right, and that's going to be this one. And that's going to go this way, and that's going to go this way. So as I am squeezing, those are those deltas from the definition. As I'm squeezing deltas around A's, epsilons are squeezing around L, and we say that the limit of f of x as x goes to A is L. The picture I have is limit of square root of x as x goes to 4 is 2. What is the limit? Limit is the y value computed. Now, do I compute at 4? No. I compute at infinitely many points around 4, right? Never computing at 4. Computing at 4 is reserved for pre-calculus. F of 4 is 2. Now, because you are never computing at 4, these calculations are much more powerful than pre-calc calculations. In pre-calculus, when the point is not defined, your function value does not exist and you are dead in the water. In calculus, if the point is not defined, we don't care, because we are calculating in all of these values before and all of these values after, and we are inferring to what the answer is without actually ever calculating the point. Now, I like to explain that as well with the bridge. Let's say, hashtag Florida, you have a collapsed section. How? Yeah, that's your engineering of C's, and 70 is enough to pass. Right? Yeah. So if the section of the bridge is collapsed, but the rest of the bridge is standing, and this is right rubble in the water, how do you fix this? Do you just teleport this section in? Well, not yet, right? Eventually, hopefully. You approach this section from the left, you approach the section from the right, and then you fix it, right? So it's that's literally what it means to find the limit. It's the approach. You are going there, and you will see what is happening there when you eventually get there. So can pre-calculus idea fix that section? No. Because there is no approach, there is no motion, there is nothing, and it's already broken. So pre-calculus cannot solve that problem. Calculus with the approach can. So now, knowing all of this from calculus 1, the most important part was that your x-axis x has this point A that x is approaching. Now, we have the Juliet approach. Juliet approach is x approaches A from the left. We put that minus on A. And the Romeo's approach is going to be blue from the right. X approaches A plus. These are known as one-sided limits. And there is that theorem which states where the two-sided limits are the same, the limit for the problem is that number. If the two-sided limits are different values, there is no limit. Okay? So this is your calculus 1, and I hope that you would label this as easy, because you understand what the approach means, you understand what computing function value means, and you can understand that you can approach from left or right, and that is it. You are on the one-dimensional line, you have one-dimensional motion to worry about, which is you can go left, you can go right. It's only one direction. Let's open the gates of hell. My domain now is two-dimensional, and I want to approach the point xy that it's, let's say, 2, 1. Let's locate point 2, 1 on my graph. There it is. In how many ways I can approach this point? Yes. Let me give you one of the ways to approach this point. Whee! What's the function of that? Turns out to be very easy, and you should know it, by the way. It's a spiral, exactly. If you go to your polar coordinates, it's going to be r equal theta. R equal negative theta, right? Because we're spiraling in. So yeah, it's a joke. But it looks terrible. Please understand that at the end of the day, we are leaving this classroom, hopefully through that door, right? There are other exit points, but so what are the ways that we are approaching that door, hello limit, x approaches, right, to leave? Now, most of you are going to, because you are sane, you're going to take a linear line approach, which on the flat Euclidean surface is the shortest distance, right? Now you're conditioned to do that. You're conditioned to do that because we kind of evolve in the sense that we want to use minimum energy all the time, right? Anything longer than the shortest path will use more energy to run the body to walk to, right? So we preserve energy by using the shortest route. So as soon as you make the corner of the desk, right, you are going to take the straight line, and that's the linear approach, and then you're out. Who says that you can't do a little sign going out? Here's the example. I'm going to leave, except I'm not going to leave as fast as you're used to it, but it works just fine. You get the idea, right? So the problem now is that we have an infinite approach. And figuring out these limits is obviously a living nightmare, right? So we know that the limits are supposed to be the y values and so on. And for the most part, when you have that limit exists, you are able to just plug the point in and treat it as a pre-calc problem and actually find the limit. The issues where we pay attention is where we have things go south. Zero in denominator, most of the time. Vertical asymptotes, right? So what is the vertical asymptote? We talked about the waterfall, right? So when we are looking to find the limit in Calculus 1, without any hesitation in Calc 1, you would say that the limit of x squared as x goes to 3 is equal to 9, because in your head you plug in 3. You are not supposed to do that. You are not allowed to do that. But it works, because the answer that pre-calculus gives must be the same as the answer that limit gives, right? Because limit is just the y value of the function. Now, x squared is nicely behaved polynomial. Hey, all fun and games, right? When is not fun and games? 1 over x squared. 1 over x squared with x going to 0. You have 1 over 0, and that's now the issue. Now, pre-calculus immediately does not exist, leave it. But calculus say no. It goes to positive infinity because left side and right side, they both hug the asymptote going up. It's positive infinity. In the sense of limit, does it exist? No, it's not a finite number. But we know that it goes to positive infinity. As in contrast to 1 over x, that does this. 1 goes up, 1 goes down. So they don't agree on a theorem. And that one we say does not exist because they go opposite way. So when we are talking now about the limit, we don't worry about nice and beautiful problems, right? Elon Musk said that in one of his interviews. Running a company is living nightmare, right? Because as an owner, you only get to deal with the most terrible things, right? And man, that's what leadership is. All you deal is just crap, right? Your employees are designing things and making beautiful stuff. And so what is your job? Conflict resolution, figuring out the money, are we going to stay open? Something exploded somewhere, right? That's it. So as a leader, it's just stress, and terrible things all the time. That's what leadership is. And you have to be strong and capable and able to withstand that, which is why the vast majority of people are not able to be leaders, because they can't deal with that stress, or they don't have management skills and skills to actually handle it at all. And you also always have terrible leaders, right, who are completely incapable, but they're still trying, and obviously the results are terrible. So, thinking about these concepts, right? Are we going to worry about nice limit problems? No, because you can just plug in, even though you're not supposed to. You plug in, you have no zeros in denominator or anything crazy happening. That's the limit. Done, right? Just like in Calc 1, x squared equals 9, done. We worry about those problems that once you do the, we call it boundary problems. Once you plug in value, hoping it's going to be nice, you get 0 in denominator. Those are called boundary problems, and they are solved in 2 different ways. Algebra, or the method that is now new for Calc 3, which is figuring out paths that will give you different answers. That's analogous to left and right approach. But see, the problem here is that you have to actually find functions that will give you different numbers. In Calc 1, you calculate left limit, the red one, you calculate the right limit. They both give you a number at the end, and then you just say, oh, numbers are the same. Oh, numbers are different. Does not exist. Now, your job is to actually find a function that will give you a number, say 7, and then find a different function that will give you 13. 7 is not equal to 13, therefore limit does not exist. So technically the same theorem is here, except it's not a 2 approach. It is infinite approach, because I can do sine, cosine, ln, square root, right? I can x square my way out, right? Depending on what I want to do. Now, if all of those infinitely many pathways are all giving me, like in this apply problem, the same result, me getting out, the limit exists. Well, guess what? I'm getting out, right? However, if one of those fails, I'm not getting out. I'm not getting out. What is the failure? A force field vertical asymptote here, right? I'm taking my paths. I'm gonna slam into that vertical force field asymptote wall every time I can't reach the door. Prison bars serve as that force field, which is made out of metal, not out of science fiction stuff, right? So you have to understand that we have, right? And they say, oh, it's limited. Of course, prison is limited because you put limits, right, in the way. So when we start dealing with now limits in 3D, we start with this picture, and then we understand that when I draw a different example, here is a nice linear function that we can use to approach the point along the linear function, like that, right? Or draw again the same and have a beautiful quadratic that we can approach this way to our function, and then you guys go and fit the modification, right, of the square root and whatever else you can fit to get to 1, and then you look at the approach. So, when the things are nice, in quotation mark, we have the problem as limit of x squared plus 9y minus 6 as xy goes to 0, 3. No 0 in denominator, no asymptotes to worry about or anything like that. Pre-calculus will do. So just plug in, we get our 0 squared plus 9 times 3 minus 6, that's 21, and 1, right? Technically, we calculated the z value, and we know that that's what the limit actually gives us. In Calc 1, gives us the y. In Calc 3, gives us the z. Right? So it's all fun and games until we get to those that are not so nice, right? So here we go, not so nice. Now, not so nice, as I said, are going to divide. We'll deal with that. So let's take a look at the first. Oh, I just remembered that I didn't give you the epsilon delta definition for the. Oh, I'll give you that after the talk. So, well, I can't do this. I skipped way too much. I started solving the limits without defining it, and then without defining interior and boundary points. So when I say boundary point, you will go, huh? So, yeah, I have to draw the line over here and stop this, and I'll come back. Definition of the limit. We know the definition from Calc 1. Now we're doing the same thing, except our domain now is two-dimensional. The entire definition is the same. So we're going to say that the limit and now we write limit of f of x, y, right, because you have x and y as input. And now we have as x, y goes to, let's say, a, b, is equal to L if for every epsilon larger than 0, there exists a disk of radius delta larger than 0, such that, and we have our standard f of x, y minus L is smaller than epsilon whenever 0 less than, and now we need Euclidean distance. It's not going to fit here, so next line, 0 less than, and this is now Euclidean distance, x minus a squared plus y minus b squared is less than delta. So this is our standard definition of the limit. And we have now the new idea of a disk rather than a length, because we are no longer on the one-dimensional x input, so that I can say this distance is delta and this distance is delta, right? Now we are on the two-dimensional domain, so around this point there is a disk of radius delta, and as you can see, the same disk would be everywhere, and the same disk has a spiraling in or a linear line through or a quadratic. So the delta now is no longer a little bit to the left and a little bit to the right. It's a disk of a very tiny radius around the point of interest. Now that gives the rise to a tube, three-dimensional tube. Yeah, great. Exactly what I need. Three-dimensional tube. So here is the point. This delta over here, radius, is extremely small. Here is the point, and I take this tube, right, and wrap it around the point, and there is a little bit on each side, but in 3D. As that goes up, it will hit the function, and it will reflect into the z-axis into a one-dimensional epsilon, a little bit up and a little bit down. The picture for that is not that great in the book, but it's the one that we have. There's no way to draw this perfectly. But here is your point of interest. Here is the disk with the radius delta that creates this orange tube, right, that will go up, intersect the surface of the shape you have, and then that intersection will shoot the z's to the z-axis to create this envelope, right, the L minus epsilon and L plus epsilon, to create a little there. Now, as you squeeze the deltas, making the circle smaller and smaller and smaller and smaller, these epsilons squeeze more and more and more and more. So the squeeze here is the squeeze there. But this is a two-dimensional squeeze now, and this is a one-dimensional squeeze. This will collapse as you are approaching the point of interest, AB. When that collapses to AB, these epsilon collapse to L, and you have your limit. So it's the same definition as we had it before. Now it's just done in 3D, and unfortunately, right, the graphs for this are not really friendly. So we're going to have some point there. There's going to be a point AB in there. The radius of this is delta, and there's going to be some kind of surface over here. Oh, there's some kind of surface over there, and that's the z-axis. So now when I shoot these and they hit the surface, they will create some kind of, they will have to follow the surface, right? So the perfect circular disk in the domain is going to be whatever kind of puddle-like thing on the surface, depending on the surface. I mean, it's just a slanted plane. It's going to be another circle or ellipse. And that is going to send these rays, the top ray and the bottom ray and the mid ray, and then epsilon distance apart for L plus epsilon and L minus epsilon. Squeeze the bottom, it squeezes the top. The limit at A and B is L. We'll continue this next week. There's much more to this, including properties and stuff. See you tomorrow.